When we find derivatives, we appeal directly to the definition. At other times, sometimes if we have nice little rules in place for finding the derivative, then we don't actually have to go straight back to the original definition. Sometimes that's harder. So I tell you what, it turns out things can be really nice if you have a function that looks of this form, which oftentimes we do, like 5x to the third plus 3, okay, or negative 2x to the 19th minus 4.5, okay. A and C are constants here. Okay, if your function takes on this form, then it turns out the derivative of it, which gives you the slope of a tangent line, is this, okay. And it's pretty easy to remember. You just lose the C. C goes away completely, and then you bring the n down, right? See the n down there? N comes down, and then up in the top there, up in the superscript in the exponent, you subtract 1. So lose any constants, n comes down, keep the a, n comes down, and subtract 1 in the top there. Okay, we can actually prove that this rule works here. To prove that it actually works, we will appeal to the definition, okay, like this, okay. Now, the definition says that this is going to be the limit as h goes to 0 of what? A times x plus h raised to the nth plus c minus ax to the nth minus c all over h, right? Because all I'm doing here is I'm putting the function evaluated at x plus h and then subtracting the function evaluated at x, okay? So it's like that. And then dividing by h. I'm going to look and see what happens to all this mess as h gets to 0. Remember, all this stuff is in the top is the difference in two function values, and in the bottom is just the difference between two horizontal values. It's just h. H is sort of our increment there. So it's just a rise over a run. Okay, that's all that is. All right, so let's see if we can carry out this limit. So, so this is the limit as h goes to 0 of a times x plus h to the nth power minus ax to the n over h, because we got a c here minus a c there. Those just go away, so we're just left with this. And now at this point, look, what I'm going to do, I'm going to invoke that binomial theorem. Binomial theorem. Okay, that's what I'm going to utilize. H goes to 0 of, I'm going to expand this stuff in a sum, right? K goes from 0 up to n. N, choose k, get x to the k and h to the n minus k, okay, and then minus ax to the n all over h, right? How that is. Okay, now let's expand out that sum just a little bit so that we can see what's going to happen here. This is pretty slick. I'm warning you. You better hang on tight. We get this is. I'll keep the a in on each term, I guess. So I'll do a times n, choose 0, x to the 0, h to the. Can I just say n minus 0 is n, and then plus the next term in the series. There's going to be a times n, choose 1 times x to the 1 times h to the n minus 1 plus a bunch more terms, however many you have there, and then the last couple terms are going to be what? A times n, choose n minus 1 x to the n minus 1 h to the n minus n plus 1, okay, and then finally a times n choose n times x to the n times h to the 0, which is 1, and then finally you got to subtract off that a x to the n, all that's over h, okay. All right, now let's see what's going to happen here. Turns out the limit of a sum is the sum of the limits, provided that the limit of the limits for each of the terms don't do something strange, go to infinity and whatever. And also it might help if you have a finite number of terms. Some strange things can happen if you sometimes the limit doesn't exist if you have an infinite number of terms and so forth. But provided everything is nice and neat, then it turns out that all this is going to be the limit as h goes down to 0 of, so I'm going to break this off into several terms here. This is a times n choose 0, x to the 0, h to the n minus 1. I'm dividing through by h, okay? Plus the limit is h goes down to 0 of a times n choose 1, x h to the n minus 2, dividing h into that term as well, okay, plus dot dot dot, plus a, oops, sorry, forget my limit symbol. The limit is h goes down to 0 of a times n choose n minus 1 times x to the n minus 1 times h, right? This is just an h there. And then, oh, got to divide through by h. That one goes away, actually. Okay. And then finally, we got this last part here. I'm going to divide that by h. So I get plus a, maybe we'll do it like this. The limit is h goes down to 0 of, maybe I'll just keep this stuff over h. Got a times n choose n, x to the n minus a x to the n all over h. Okay, and we are golden, because you know what? Look at what happens is h goes to 0 here. All this stuff goes to 0, right? Think of what happens if h gets really small here. H gets really small, all of this gets really small. This is going to 0. So h gets really small here, all this is going to 0. Look what happens down here. N choose n is just 1. Okay. So this is a x to the n minus a x to the n, which is just 0. 0 over anything is 0. Okay, so it doesn't matter as h goes down to 0. This is approaching 0, 0, 0, 0, 0, 0. Okay, so all of this limit is 0, and you're just left with whatever this stuff is. Oh, there's no h in here. So what happens to this stuff as h goes to 0? We don't care. It's just a times n choose n minus 1 times x to the n minus 1, but n choose n minus 1 is just n, so this is a n x to the n minus 1, and there it is. We're done. Ta-da! That's exactly what we said it would be. Okay. And look, it's kind of nice here, right? Because you see how we've used the binomial theorem to expand this power of this sum in here. And now, anytime we see a term that looks like this, and which turns out it's going to be pretty common that we see stuff like that in a lot of our regression models, if we need to differentiate it, we know a quick, slick way to go about doing it. Okay, we don't have to remember all this stuff about differentiation. We just remember the rule.